In different kinds of applications and data, of course, sometimes two-dimensional plotting is not enough to represent what we would like to see in the graph. And that's why now we will have a look at three-dimensional plots in Matlab. So the three-dimensional plots, basically we can divide into two different types. So one is three-dimensional line plots. And that basically means that we are talking about a curve that we would like to represent in 3 dimensions. For instance, if you have a piece of cable that when you put on the table, it kind of is bent in different ways and it just lies there. So if you were to represent that kind of, if that cable is a line, then we talk about three-dimensional line plot. And for that purpose, we have the plot3 command, which works practically the same as the two-dimensional case, so the normal plot, with the difference that now we talk about three axes in here. So we have to represent axis x, y, and then z is the kind of resulting value that comes up in the third dimension. That one can also be called similarly to the plot case. You could say plot3 and then put just z in here. So then it works like in the plot case that when you don't specify x and y, then Matlab will kind of represent them naturally just by giving indices 1, 2, 3, and so on for the given z points, but now on both axes. However, you cannot, for instance, say plot 3 and then maybe just x and z. Then Matlab will complain and say that we would have to run it for me to remember what the error says, but it might say something that not enough input arguments or something of that kind. Now, the good thing is that the properties of plot 3 can be controlled in the very same way as in normal plot. So you can have line specifiers for what style of line, is it solid, is it dashed. You can modify the thickness of the line, you can add the points to be also plotted along the line and so on. So all these line specifiers and any other properties work in plot 3 exactly the same as they do in normal plot. So let's have a look at an example. Now this is a mathematical representation in a parametric way to draw a spiral in 3 dimensions. So of course in 2 dimensions you just look at something like that. But now the equations I have given are actually for 3-dimensional ones. So you could actually kind of pick it and rotate around and see that it's in 3 dimensions. So what we have to do is define x, y, and z in here, and this so-called parametric representation means that we actually have only one parameter to which we give a range of values, and then that one we will plug in. And then as we plot x, y, z all together, we will get that spiral look. So let's do it. We start from defining pi, or our t, sorry, which was from 0 to 6 pi. We will use some small step size. Then we had, sorry, this should be a column. Then we have x is square root of t times sine 2t. So sqrt of t, and then times sine of 2 times t. And once again, we are in the world of vectors and matrices. So that means that now, since t is a vector, square root of t is a vector, and then sine of 2t is as well a vector. So this multiplication will not work in that way, but it will work when we add the dot, because it just means it takes one by one every value of t and evaluates this formula for that particular value. So now then x becomes a vector as a result. Same story for y. Y, same thing but with the cosine, so I'll just borrow this piece and change sine to cosine, and then Z was just 0.5 times t. Alright, so we have our XYZ calculated, and now we want to plot it in 3 dimensions. So plot 3, X, Y, and Z. So this is the very basic we can do. And there we go. So you see, it's a spiral, which actually now, when we pick this rotate button here, sometimes it takes a few seconds for Matlab to catch it. Yes, now you can see this kind of circular arrow. So now when you grab the graph and start spinning it, you can actually look at it from different angles. And you can also, now it looks more like a ball, you can also flatten it to just 2 dimensions. So when you do it sufficiently, now you see there is some z-axis, but it's possible to actually flatten it. Yeah, like now it's only x and y. So whenever you feel like that particular view is the one you want your graph, then you save the figure with that position. So this is the nice part, that if the initial kind of default way the 3-dimensional plot comes up is not very easy to read and to understand, you can just move it around a little bit to find the profile you like the best, and then save it like that. So as I said, the properties, we could make the line thicker, for instance. Also 3-dimensional plots have the grid possibility, so we can actually add some grid lines, maybe for better readability of our graph. So now you see the grid, and then of course labeling. So we have X label, just call it X, Y label, and the Z label. Yeah, so now the labels are there. Let's see what else is there. Well, basically that would be it. So as I said, also you can have the, if you remember on 2-dimensional plot, we could add also kind of the points together with our line. So now this would mean those points which are there defined with the line. Now they are relatively dense. So for instance, if I try to use, let's say, asterisk and the line, it may end up just being a very thick line all the way. Yes, maybe you can slightly see the asterisk. But if we actually reduce this, maybe like that. So yeah, now you can see better. Of course, it's still quite round for us, but in reality now what connects those points are just straight lines. It's still fine enough for us to be able to say that actually this is a nice and smooth spiral. Okay, so that's when it comes to line plots in 3 dimensions. But the second family of plots that we may want to see is surface-like plots. So surface is if you take, for instance, a sheet of paper and you keep it in the air at different angles, you can bend that piece of paper differently. Or for instance, if you think of a horse saddle, which has that shape kind of curved in 2 different directions, in one direction it's curved upwards, in one downwards. So this kind of plotting a surface is another family of plots, and that one needs a small trick to be done for the plot to actually work out. So how is it done, and why? What's the trick and why it has to be done? Basically, we have to create a mesh grid for our plot. So what does it mean? Initially, I just define for which range of x and y values I would like to see my graph plotted. So that means that if this is the third dimension, so we have x, we have y, we have z in here, and then I'm just specifying that my x is this and my y is this. And I give those just as vectors. So here I say from -1 to 3, then y is from 1 to 4. So I'm basically giving Matlab just like a piece of information that where my x points would be and where my y points would be. But this is just like one-dimensional and one-dimensional. And our z plot is supposed to be surface plot, which is actually in 3 dimensions. So that's why we have to use this command mesh grid. And now what it does is that it combines, for instance, for every value of this vector, it combines it with every value of this. So for instance, for x equal -1, it will kind of create pairs of points, -1, 1, -1, 2, -1, 3, -1, 4. Then it goes to the next value of x, which is 0, and it will be 0, 1, 0, 2, 0, 3, 0, 4, and so on. So basically, this mesh grid command, it changes x and y into matrices which create those kind of pairwise comparisons, so or pairwise combinations of the points, so that then our whole xy surface has now a set of points represented for every point from the x and y vector individually. Let's look at this example and what does it actually mean. I will comment this part. So now I had x changing from -1 to 3 and y changing from 1 to 4. And we use that mesh grid. So I will use now capital X and capital Y because they become different variables. They will now become matrices. So that's and mesh grid XY in here. So let's run it and see actually numerically what that means. So you see, it turns them into matrices which are kind of copies of themselves so that they can be combined with their respective values. So for instance, as I said, when x first value was -1, then Matlab combines it with every possible value of y that we had. Then when x is 0, the same, and so on. Or you look at it the other way. When y is 1, then it gets combined with every possible value of x. So that's what this mesh grid actually does for us. And in that case, it means that now we can have calculation of our z, so that shape in the 3D that we want can be calculated using those capital X and Y matrices. Now let's see what was the formula for z. So we had x times y square, x times y square, and divided by x squared plus y square yes, so now once again x, y are matrices, and so once again we need to think of the element by element operation. So we don't want to square x matrix in the algebraic way. We want to square it just its elements. We want to square all its elements individually. Same for matrix y, then same for matrix y in here, and then since x is a matrix and y squared is a matrix of same size, then their multiplication can also be only possible element-wise. And finally, now this upper thing is a matrix, and this one is a matrix, so division of those is possible only element-wise as well. So remember to have your dots everywhere where you should. If you don't have, you can expect that Matlab will give you a hint that there is an error somewhere. The resulting Z matrix is exactly same size as X and Y. So if we go here one by one, size of X is 4 by 5, size of Y is 4 by 5, and size of Z is 4 by 5, sorry. Okay, so yes, let's see what happens if one of the dots is missing somewhere. Okay, actually it did that division, yes, because possibly that division was possible when we talk about different sizes, but you see now the result is actually 4 by 4, so it's something else. I've accidentally removed the dot, which doesn't make much problem, but it creates a completely different result from what should be. I removed that one in the square, so you see once again it tells here error using the power, incorrect dimensions for raising a matrix to a power, check that the matrix is square and the power scalar, and to perform element-wise matrix powers, which is the case here, use dot power. So there it is. Okay, so we have our Z calculated, and now we want to do the plotting. So now once the mesh is ready and the Z points are given for all the grid points, we can use any of the surface plots. And there are different ones. There's a list in here. So that, for instance, surf is for surface. Then there is mesh. There's mesh itself, and actually then there's mesh Z, mesh C. These I don't remember myself how they differ, but we can run them and see what they bring out and how they differ. So figure, let's see, there is actually 7 of them plus the regular mesh. So I'll make it like this. I'll put in the names. So we mesh. Then there's surf. Mesh Z. Mesh C. Then we have surf C, surf L. And then waterfall. And finally contour 3. Okay, so I have them in here. Let's first do just a simple mesh. So the command is just mesh, and now we give X, Y, Z. So X, remember it's the capital X, capital Y, and capital Z in this case. So let's just see the mesh first. Yeah, so you see it's like a kind of like grid, like plot where the colors of the lines here are actually adjusted to the values. And then the inside of those is white. And that's major difference from surf plot is that in surf actually the surface has colors based on the level of our data points. And you see this plot is relatively rough, but if you want it a bit less rough, you can add some more steps in here. That of course means that there are many more data points to be evaluated, so the calculation may be heavier, and the plot of course is heavier, but it's worth making it at least with some level of precision. So now it's nicely smooth already, at least for the first bare eye look. Okay, so let's try and see those different figures here. So we have subplot. Let's make them 2 by 4. So the first one again is just mesh. And then second. Now I have to copy them because those plot names are separate in here. So surf. maybe let's combine those mesh next to each other, so we would have mesh Z, mesh C, and then let's make waterfall, and then we combine the surface, so we surf, and then we had surf C, surf L, and contour 3. Okay, let's run. It will take a while just because of the plots. Combine 8 plots like this is relatively heavy. So now we can see what that actually made. So we had mesh Z was, so it's actually kind of creating a wall here where kind of connecting the surface with this kind of wall on the Z dimension down to our XY axis. Mesh C combines it with a two-dimensional contour plot on the XY surface, and this is a regular mesh. Then we had, this was waterfall, so actually it means it's going, it's kind of creating the mesh, at least it's plotting the mesh just kind of in one dimension, even though the calculation is of course done for both. And then this was regular surface C, which was the one combined with contour again. Surface L, that we probably would have to read from help what it means. That may be just about the range of colors in here, and then three-dimensional contour. So this one is as if we have kind of sliced our surface kind of in third dimension, so in Z, and then we see those lines appearing in 3 dimensions. So for instance, this kind of surface plot combined with contour you can also do yourself by making first mesh plot itself, then you hold it on, and then you just make contour plot, which is just called contour. This was 3-dimensional contour, so you see it's 3D, but contour plot also exists for 2 dimensions. All right, so this would be very generally about 3-dimensional plotting. There's also a few other specialized 3-dimensional plots. So for instance, you can draw a sphere, you can draw a cylinder, you can draw 3-dimensional bars, you can draw 3-dimensional stem plot, 3-dimensional scatter plot, 3-dimensional pie plot. So really, once again, based on the type of data you have and how you feel like representing it is the best and the most kind of legible way, then it's your choice which plot you choose in here. And they are all in help. So help also does have examples which help you try it out first on some ready example, and then you try to adjust it to your own application.